So for the final, I had told you that it's going to be cumulative, right? But of course, I'm going to focus more on the second half of the class than the first one. But let's start with the first part. So from the first class, I would say things to have into consideration are, of course, this slide, the use of scientific method, right? So why do we do research methodology, right? Just understanding that there needs to be a methodology to do the research. Okay. PICO question, of course, population, intervention, exposure, comparison, and outcome, right? Like I said, I is for intervention, but we can use it as exposure for the types of studies that we are doing, except when we're doing, for example, an experimental study, which would be, of course, an intervention indeed, right? And then knowing that to the PICO question, you can add the T for time, and that will be especially helpful in clinical research, right? So just like we did in the EBP, like the poster presentations, the population, of course, we always want to be like very clear on the population that we are looking at, right? But something that we didn't talk about that we should have is population is not just the people that we're looking at, is the context that we're looking, like in what context we're looking at the people. Okay, so if I'm doing a cohort study, we should always accompany by let's say adults 18 to 35 years of age, whatever, during 2026 in this location. Okay, so population is everything that goes with who we're looking at. Okay, then for exposure, of course, we have let's say we're looking at let's see, let me see one of the examples. Sunscreen and skin cancer. Okay, so before is my exposure would be sunscreen, and it can be many things if they apply it or they don't apply it. How often do they apply it? What concentration are they using? Right. Comparison. It could be compared to. I could do comparisons of two types. So I could compare to a group that doesn't use sunscreen or to a group that uses SPF 30, right? Versus SPF 70, if I want to see the differences, right? An outcome in this example would be skin cancer, right? So, like we said in other classes, like defining your variables is always going to be very, very, very helpful and needed, right? Um, let's not do this. Oh, okay. Boolean terms. And what will and do? Would it expand your search or narrow it down?
Expand.
Yes. No, actually, no. And will narrow it down. Because for and, you're making it a condition that both have to be present, right? So if they both need to be present, your number of articles may go down, right? Because you're putting more and more conditions. With or, it's going to show you everything that includes these or these. So you're expanding it to anything related to this topic and anything related to this other topic, right? If we're using parentheses, and parentheses is very common, what will the parentheses do? It will refine it, right? It will refine your search. And you could do, for example, you can use an and Boolean term within a parenthesis and then an or. So it will show you everything that has everything in the parentheses. Let's say we're doing sunscreen and solar exposure. I don't know, sun exposure in a parenthesis, and then or skin cancer. So it's going to show you everything that has sunscreen and sun exposure or just skin cancer. So if they're looking at skin cancer and if they're looking at sunscreen and lung cancer, I don't know, whatever, it's going to show it to you, right? Even if it doesn't have skin cancer. And then it's going to show you another result for skin cancer alone. Does that make sense? Okay, good. Okay, epidemiologic transition and demographic transition. Do you guys remember this one? No? So the epidemiologic transition is just the different patterns in morbidity and mortality because of the diseases. So for infectious diseases, for communicable diseases, and how we moved from a lot of infectious diseases in the past, and now we're on a more chronic disease era. Okay, so we have now more chronic diseases than infectious diseases, right? And before in the 1800s, we had more infectious diseases than chronic diseases, right? Life expectancy was lower. Now life expectancy is longer, so we can expect more um, chronic diseases, right? And demographic transition is just that transition which talks about birth rates and death rates. So it tells us about how a country can go from, if you have a lot of kids and then you have very little adults, it will look like a pyramid, right? And if you have like aging populations, you will have an inverted pyramid. Remember we talked about that? Okay. So that one will go into the exam. Of course, you always want to know the difference between epidemic and pandemic. And I don't think I'll do any history, to be honest. Okay, let's do class number 2. Always very important to remember, population is everyone, right? And we call it capital N. Oops. And in a population, we will look at parameters, which we cannot calculate, but we will have parameters from samples, right? From sample statistics. So in samples, we do calculate statistics, right? And then for samples, we say that it must be representative. And then that process in which we estimate is called, when we estimate from the sample to the population, what is it called?
Sample.
Sample is the people that we choose, right, from the population. And then we're going to do statistics. We're going to calculate statistics on that sample. And then we're going to use that information from the sample to generalize on the population. What is that process called?
Parameter.
Parameter is what we're going to estimate from the statistics, but it's called inference, right? No? It was on the exam. Okay, so we're gonna infer from the sample to the statistic, right? And then this is just that we have different types of samples. So we have random sampling, everyone has the same chance, right? We have stratified sampling, in which we divide by groups based on the characteristics that they have. So I would use stratified sampling if I was doing, let's say, by age, right? And why? What is the goal of this? That each group will have different weights so that they are all equally representative, right? So if I know this group, the age of 20 to 24 is smaller, I will give it a bigger weight on the calculations so that it's representative to the, let's say, 30 to 60. Okay? So that's why I stratify, because I want the sample to be representative, right? Then systematic sample is when I say every 3 or every 4, I'll choose it for my sample. And cluster sampling is more like in now I won't look at the individual, I will look at a group as the unit of analysis, right? So remember when we were looking at the NHANES, for example, they were the primary, the PSUs were clusters, right? They were like neighborhoods, right? And they were looking at a neighborhood at its as the unit of observation, right? That was the first part of the NHANES. So that would be cluster. Okay, very important variables. Qualitative versus quantitative, right? So qualitative will be the categorical variables. Quantitative will be the numerical variables. In the qualitative, we have nominal, in which we don't have an order, right? All dichotomous qualitative variables are going to be nominal. So, of course, that will be yes or no, right? But it can also be if I am exposed to the sun more than 6 hours or less than 6 hours. That's also a dichotomous variable, right? Even if I can count the hours, I separate it in two categories, right? So that's dichotomous, so nominal. And then ordinal is when you have a logical order. So if you have education, you have middle school, high school, um, undergrad, master's, postgraduate education, right? That would be the logical order. And then in the quantitative, we have discrete that are finite, right? So how many dogs do you have in your house? 3, 4, 5 dogs. And then continuous, like GPA. GPA could be infinite, right? You can add as many decimals as you like. Age usually is continuous. You can be 18 years, 3 months, 4 days, 5 seconds, I don't know, right? It can go on and on and on and on, right? Okay, let's practice. Marital status. What is marital status?
Nominal.
Yeah, qualitative nominal. There's no order to it, right? What comes first, single or married? You cannot tell, right?
Yeah.
But if I do age in categories, 0 to 10, 11 to 20, 21 to 50, more than 50.
Ordinal.
Qualitative ordinal. Okay, number of children.
Discrete.
Hmm?
Discrete.
Yep, quantitative discrete. You cannot have half of a child, right? Weight in pounds.
Continuous.
Yep, continuous. Good. Okay, just as a reminder, these are the different graphs, right? So bar charts we use for qualitative variables or discrete variables. Histograms were used for continuous variables. So if I were to look at systolic blood pressure, at weight, at age, I would use one of these, right? When would I use a trend graph or a line graph?
Do comparison.
Yes, but you'll see it more often in cross-sectional studies for prevalence. So this is a great way to compare prevalences across time. This is the best, like a great way to summarize it. And then pie charts will show you proportions. Okay. Mode. Number occurring most frequently. So the number that happens the most. Median, the one in the middle. So if you have an odd number or an even number, then it changes on how you calculate it, right? If you have, let's say, 4, you take 2 and 3 and you add them and then divide them by 2. And that gives you your median. Okay? Mean is just the sum of all the values divided by the number of values. So if I have 10 patients, I'm going to add the measures that, let's say we're doing mean BMI. I'm gonna add all the BMIs of everyone, right? And then I'm going to divide by 10, right? Standard variance. Actually, I won't ask variance. That's fine. A normal distribution, it looks like a bell, right? Symmetric. In this one, I can report the mean, the median, and the mode, and they should be the same, right? But when I have a skewed distribution, I can have a skewed distribution to the right. So you see, to the right means like that the tail is on the right, right? So you call it a skewed to the right or positively skewed distribution. To the left, then it's going to the left, like the longer part of the curve, okay? So this one here, wait, do you actually see my cursor? Yeah? This
Yes.
one here, is it to the right or to the left?
Left.
So is it positive or negative?
Negative.
Exactly. So then what happens? Since now my middle number is not gonna be on the middle, like this one, right? It's gonna be here. But my mean, because most of my values are on the left, is gonna move to the left, right? So I need to know which one to report. If I have a skewed distribution, the best value of central tendency to report would be the median, okay? The median. And this is called a multimodal, right? Okay. Uh, Pearson correlation coefficient. It's just telling us there's an association. It's not a causal association, right? It's just telling me that there's a relationship between two variables. It doesn't even have to be it doesn't have to be like the exposure and the outcome. It can just be any two type of variables, right? Um, Knowing what you know, when would I do a, a Pearson correlation coefficient? If I want to test for what? Think
Is it
of a
like a line graph to see
Yeah,
like
we're gonna find a line graph, but I would do it if I wanted to see if a variable is associated with both the exposure and the outcome. And what is that called? Anyone remembers? A confounder, right? Is that what you're gonna say, Alex?
No.
Okay, so if I have a perfect direct linear association, I'll see a line like this, right? It can be a positive association or a negative association, right? This would be a perfect inverse linear association, or I could see no association at all. So there's no way I can make a line here, right? As opposed to here, where I see all of them going up. Yeah? Okay, my favorites, contingency tables. What is A?
um A is they were exposed and got the disease.
Yes, perfect. So then B are exposed but did not get the disease. C are those who were not exposed but still got the disease. And D, those who were not exposed and did not get the disease. Why is this useful? It's going to let me calculate odds ratio, risk ratio, right? The relative risk, the incidence, the prevalence, everything. I need this table for everything in life. 1 second, my computer is going to die. Sorry, guys. Okay. Okay. And then of course, knowing how to do the table. So exposures go on the left, right? And then disease status will go up here. Okay. Class 3, let's see. Just as a little reminder, ratios, rates, proportions, percentages, right? So in a ratio, my numerator and my denominator are not contained within one another, right? In my rate, I have a value of time, right? My denominator is a measure of time. In my proportion, my numerator is part of the denominator, right? So a proportion would be uh, how many cases of COVID were in the whole world. Cases of COVID would be included in the whole world, right? A ratio would be how many cases of COVID versus how many cases of influenza, right? So two different measurements. And then a percentage is just a proportion times 100. Can you think of an example of a percentage in one of the measurements that we do? Prevalence. Prevalence is the easiest example of percentage that we need to do. So my numerator, people who have disease, all the new cases will be included in the denominator, who is total population, right? Okay. Incidence. Number of new cases during a time period over total population at risk as at the start of the time period times the multiplier. So if someone already has the disease, are they at risk? Not anymore, right? Unless it's like an infectious disease or something that can happen again. But for the most part, they won't be. So if I have ovarian cancer, my new cases of ovarian cancer is 2. My total population is 100. Males is 40, females is 60. Who is my population at risk? Females, right? Okay. Um, okay, let's see. Incidence density. This one will come on the exam. So incidence density, we can use it during cohort, like for cohort studies. Okay, so it's a variation of incidence rate in the, but the denominator will have a percent time. Okay, so numerator will be the same, the number of new cases, right? Divided by the total percent time during the time period. So if I have this table, I have the time variable on the x-axis, right? So I have 0, 1, 2, 10 years, right? So let's say my cohort study was up to 10 years. Ideally, I would have followed everyone for 10 years, but that doesn't happen in cohort studies, right? Because of loss to follow-up, because they get the event, because they die, because they leave, whatever, right? And then on the left, I have my people. So let's say person 1, I follow them for 6 years until they got the event. Number 2, I followed them for the 10 years and they never got the event. Number 3, they joined the cohort late. So I started following them on year 2 until 10. How many years? Eight, right? Because if they started at year 2 and I follow them until year 10, I follow them for 8 years, right? Number 4, I started following at year 0 until year 3. How many years did I follow? 3, right? And then they left the study for whatever reason. Okay. So then you look at the people who got the event. Those are going to be my denominator, right? People who got the event. Why are the people with the D who are deceased or L to loss of follow-up not part of my numerator? Because I'm looking at incidence, right? And incidence is just new cases. Yes? So 2 is my numerator, and then my denominator is going to be the sum of all of these person year or person time measurements. So all of the time I follow them. So 6 years from the first person plus 10 years from the second person plus 8 years from the third person, blah, 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 right? And then you end up having 2 divided 75. 2 divided 75, that's 0.027 when I round up. And then I use my multiplier, and then I could say 0.027 cases per person year, but ideally when I do the multiplier, I'm going to be able to say 27 cases per 1,000 person per year. Okay? So this sounds better, like the 27 cases per 1,000 person or people per year, right? This is more impactful. This is easier to digest than 0.027 cases per person year. Yes? Or no? Okay, good. Prevalence, all the new cases.
I'm sorry.
Yes,
Can you go back to the last one?
yes.
So it's 2 subtracted by 75.
2 divided by 75.
Oh,
And
okay.
why
Yeah,
why
sorry.
2? Because only 2 got the event, right?
Oh,
And the
oh,
75 I got from adding all of these up, all the person years. Yeah? Okay. And then I like multiplied by whatever multiplier I decided. Okay, prevalence, the old and the new, right? Divided by everyone total population, right? So old and new cases. So if I have 2 new cases of ovarian cancer in February, and I had 3 in the rest of the year, how many do I have? 5, right? Divided by 100. Okay. When I look at one, let's say, day, specifically, it's going to be point prevalence, right? It doesn't have to be a day. It can be like 1 month. You can say in February of 2025 or in April of 2026, whatever, right? Point prevalence would be all the cases in a period of time. So when I say point prevalence is when I say today is what happened before today, and I'm not going to take into account what happens after today, right? But when I look at a period prevalence, I'm setting the time, I'm setting the period of time. So I'm only going to look at cases that happen within that period of time. So if I'm going to say February of 2025, I'm not going to take into account what happened in January, for example. Okay? And then again, I'm looking at the old and new cases. Correlation. So prevalence will be as like it is very associated with the incidence and the duration, right? It depends on the incidence and the duration. So if I have a high incidence, but my duration is very short, people who will be getting the disease will also be getting recovery or death at the same rate, right? So I'm not going to stack the cases up. If I have a high incidence, let's say, but the duration is very long, my prevalence bathtub is going to get filled up very quickly, right? Because people are just staying there with the disease. They're not recovering, they're not dying either. They're just staying with the disease for a long time. Yeah? If it has, for example, a very high death rate, then the incidence is high, the prevalence could be low, right? Depending on how the incidence is really. But then if the death rate is very high, it's gonna make the prevalence even lower, because even if so many come in, more of them come out. That sounds so bad. That does make sense? Okay, cool. Let's see. And then mortality, just maternal mortality rate. I will give you this formula, but know more about maternal mortality, like actual information about maternal mortality, okay? Who does it affect the most? What has happened with the rates? It has doubled since 1999, okay? And what does that mean for public health? Okay? Let's see. That's it. Oops. Okay. Levels of prevention, super important, guys. Primary, secondary, and tertiary prevention. We saw this more last class, right? But again, primary prevention is when we're trying to do health promotion. A disease has not happened and we're trying to prevent it from happening, right? So vaccines, fluoriding water, exercising, eating healthy, that's all primary prevention, right? In the secondary prevention, the disease has already happened, but we're trying to reduce the progression of the disease via an early diagnosis and treatment. What is the most common type of secondary disease?
Screening.
Yes, thank you. So we know there's a bunch of things about screening that we'll see later. And then the tertiary prevention is when all the clinical symptoms are already there. So what we're trying to do is recuperate the health that was lost, right? So rehab, treatment, let's say radiation in oncology, all of that would be tertiary prevention. Okay. Let's see from here. Just a little reminder of surveillance. Oops, wrong one. Of surveillance, right? So we want to be able to keep tabs on what's going on, right? Through surveillance. So we have all of these different surveillance systems, the behavioral risk factor surveillance system, the National Health Interview Survey, the National Health and Nutrition Examination Survey. And what we're trying to do is we're trying to keep count of our population, not like how many are they only, but how is their health status, right? So that's why these are done annually, every 2 years, every 10 years. All the time we're looking for new data, right? Everything that is self-reported is going to be cheaper and it's going to allow you to have larger samples, but your results are not going to be as accurate, right? If you have measured data like lab test results and when you measure height and weight yourself, you have more accurate and smaller samples, right? For the census data, you'll have very complete data, but limited variables because you cannot take into account all the variables, right? And then with global data, you'll have standardized results, which is good when you are trying to compare within countries. Okay. Social determinants of health. Just know this, that there are distal, intermediate, and proximal social determinants of health, right? So the proximal will be the inherent of the person, so the behaviors, the capabilities, the attitudes, and of course the direct biological threats to health. So if someone smokes, if someone drinks, whatever, that would be proximal. Yes. In the intermediate, it's more the relationships, the social context. So the community factors, where they work, where they go to school, their family, the social environment. And then we have the distal factors, which are the cultural, political, and infrastructural causes. So their education, their income, their housing conditions, their access to food, to water, to road safety. So if someone lives in a food desert, if someone lives in a cold area, right? If someone lives at the wrong side of the highway, stuff like that is distal, right? Okay. And then know the different types of social determinants of health. Although, like if I ask you for examples, you would know where to categorize that, right? So for this one, what I'm gonna do is I'm gonna just put a paragraph and you tell me which of the variables are proximal, which intermediate, and which are distal. Okay. Person, place, time, right? Descriptive epidemiology. We want to know the who, when, and where in order to later understand the why with the analytical epidemiology, right? So, of course, we have the case report, just one, the case series, a bunch of them, and then we have the cross-sectional studies. But in cross-sectional studies, you can also do cross-sectional studies in analytical studies, right? So for a descriptive study, I would only do a prevalence. And when I'm doing an analytical study, I would do an odds ratio, right? Advantages of cross-sectional studies. It will give you a prevalence of the exposure and the disease at the same time, right? Because it's a snapshot of the population and it will measure current health status of a community. And this will help you on health planning, right? It's fast, it's inexpensive, you don't need any follow-up. Disadvantages, same advantage of the prevalence of the exposure at the same time. But now the issue is you don't know what came first, right? So you cannot make any causal inference. You cannot make any causal associations. And then it's subject to the prevalence incidence bias. And what is the prevalence incidence bias? Also called Neiman bias, selective survival bias. And do we have an example here? No. It's just saying that people who are healthy are more will more likely participate in studies than people who are sick already, right? So you will have weird results on the prevalence if it's a very rare disease, for example, right? Okay, person variables: age, sex, race, ethnicity, socioeconomic status. Place variables: we have international, national, urban, rural, localized patterns. Who remembers what this map was for? I mean, it says right there.
Lyme disease.
Yes. So where is Lyme disease more prevalent?
East side, New Jersey.
Yeah. Yeah. Northeast, right? Time variables. We have secular trends. So secular trends are those gradual changes in the frequency. So we see how it slowly starts increasing or decreasing, right? It's gradual. In the cyclic or seasonal trend, increases and decreases in the frequency over a period of several years, but it's always during the same time of the year or during the same environmental factors, okay? Okay. Association and causality. Okay. what do we want to see? That there is causality, right? That is our goal at the end of the day. To determine potential causal associations between exposures and health outcomes, right? So how are we going to do that? We have the epidemiologic triangle, in which we want to be able to show that the host, the agent, and the environment are all connected, right? And with the web of causation, we can show all the other risk factors or all the other social determinants of health that are exacerbating certain diseases, right? So from this one, just study the causal pi model or the Rothman model, right? So what does it say? A whole pi, it's called a sufficient cause, right? No? Okay. And then for probabilistic causality, what do we have? P-values, right? So p-values are going to be the results of my hypothesis testing. You have the null hypothesis and the alternate hypothesis. The null hypothesis will be how you phrase it, even though what you want to see is an alternate hypothesis. Does that make sense? Right? So we're gonna frame it as there's no effect, but because this is easier to show epidemiologically, but what we really would like to see is that there is a change on effect. And then we have one-sided and two-sided hypotheses, right? The one-sided is that where you're saying it either reduces or increases the risk. And then in the two-sided hypothesis, you just says that it affects the risk, whether it's up or down, it just affects it, right? This is also easier to show because you have more space to have results on, okay? Okay. And then your p-values. If you have an alpha level of 0.05, anything that is equal to that or lower, it's going to have a statistical significance, right? What does a statistical significance means? That more likely it is not due to chance. And that is what I want to be able to show, right? That my results are not due to chance, right? So if I have 0.05, it's going to be statistically significant here. It's going to be statistically significant here, right? When the alpha value is 0.1, but it's not going to be statistically significant if the alpha value is 0.01. Why? Because it's higher, right? Than 0.01. Let's try this one, 0.008. Who wants to try it?
I'll do it.
Go. Is it statistically significant here?
Yes.
This one?
Yes.
And this one? Okay, good. Okay, Bradford-Hill's criteria. Just read it one more time, okay? What is this trying to tell us? That even when we find statistical significance, we need to be able to show that it is because one of these factors is associated, right? So if it's because the dose response, that's a biological gradient. If it's because the odds ratio is very high, that would be strength. If it's because same results have been shown in all over the world, that's consistency, right? If it's because there's a very specific association between an exposure and an outcome, let's say asbestos and lung cancer, that would be specificity, right? Okay. How to read an article. So this is like how to critically analyze an article. If you think all the parts are there, the introduction, methodology, results, discussion, and conclusion, right? And if it's telling you what you need to hear. Okay. Now we move to analytic epidemiology. right? So we have the descriptive epidemiology that we just saw, and then we have the analytic. We have the observational studies that are ecological, cross-sectional, case control cohorts, right? And then we have the experimental analytic, which is the clinical trial and community interventions. And there are so many more types of experimental, but we're just going to see these two. Okay, important things about observational studies. You have no control over the exposure, no randomization, and there might be confounding, right? Because you're just observing, you're not you cannot intervene within any of the groups, right? You cannot decide who's going to be exposed and who's not going to be exposed. Okay, first one, ecologic study. So the unit of analysis is going to be a population, right? It's not going to be a person, it's going to be a population. And every dot is going to be called an aggregate, right? What's the biggest issue of the ecologic studies? The ecologic fallacy, in which what you observe at a group level may not be true at an individual level, right? So in this one, why is the dot of India bigger than the dot of Myanmar?
Because the gap,
What gap?
the gap between like the people in different social status, like
I
income.
think it would be more, okay, yes, it could be income related. I think in this case, it's more of amount of people in each country. Okay, but good. And then again, A, B, C, D. Why? Because we're going to calculate odds ratio, risk ratio, incidence, prevalence. Case control. What is important about case control? You start with people who either have the disease or don't have the disease, right? You start with the outcome and you're going to look retrospectively to see if they were exposed to something. So you're looking at one outcome, but could be looking at many exposures, right? It's common in rare diseases. Choosing controls can be hard. So what you do is you try to match them. Of course, not always possible. And what do you calculate? The odds ratio, right? So this is what is going to give us an indirect estimate of the risk. And then it would be the odds in the cases divided the odds and the controls. And then when you do your math, you end up with A times D over B times C. So odds ratio, this is the formula, A times D over B times C. If you have an odds ratio larger than 1, you have a positive association between the exposure and the disease, less than 1, a protective factor. Can you say that if you have an odds ratio of more than 1, you have a risk factor? No, because you are not attributing risk. You cannot say that there is a risk factor when you cannot even measure the risk, right? You can measure the odds. So how do you interpret that? Let's say I had an odds ratio of 15, very high, between the use of sunscreen and the development of skin cancer. So the odds of skin cancer among those who did not wear sunscreen, right, is 15 times higher than among those who wore sunscreen. Or I could say the odds of disease among those who wear sunscreen is 15 times less among those who don't wear sunscreen, right? It depends on what is my exposure and what is my non-exposure, right? Okay. It's great with low prevalence conditions, quick, easy, usually inexpensive. You need smaller number of subjects. You just need to make your controls comparable to your cases, right? Disadvantages, you have a bunch of bias, right? You have recall bias. You may not have representativeness. You are doing an indirect estimate of the risk, right? And temporality is also an issue because you'll never know for sure that the exposure came before the outcome. And okay, cohort studies. Now we're looking at studies that start from an exposure and we follow them on time to see if they develop an outcome, right? So now I'll be able to track an incidence, right? Within cohort studies, you have cohorts, which are the group of people that you follow over time. You can have prospective cohorts. You can have in the prospective cohorts, this is today. You start with the exposure and then you follow them to see if they got the disease. This is the more common, right? You got the retrospective, in which you go back blindly to see if there was an exposure in the past, and then see in their medical histories if there was an outcome also in the past, knowing that you got to start before the outcome started, right? Because technically you have to start with healthy individuals, right? Okay. What do we calculate in cohort studies? Relative risk. So using the incidence of the exposed and the incidence of the non-exposed, we can calculate the risk ratio. How do we do the incidence in the exposed? These are my exposed, right? So the incidence in the exposed would be those who got the disease among all those who were exposed. The incidence in the non-exposed, those who got the disease among those who were not exposed, right? Oops. And then I do A over A times B divided C over C plus B. Again, this is starting from the fact that your exposures are here and your diseases or outcomes are here. If you do it the other way around, then it's going to change completely, right? Interpretation. Now you can say if it's more than one that you have a risk factor because you are attributing a risk. If it's less than one, you have a protective factor. And what happens when you have a relative risk of one or an odds ratio of one? You have no association between the exposure and the outcome, right? And how do we interpret it? The risk of skin cancer among those who don't, or among those who wear sunscreen, is 15 times lower than among those who don't wear sunscreen, right? What else can I calculate? Attributable risk, that is going to quantify the excess risk associated to the exposure, and population risk difference, that is, if I took the exposure away, how many cases would I really have? So this is going to tell you the benefit to the population by modifying a risk factor, right? And then formulas, you still need the incidence in the exposed minus the incidence in the non-exposed, that's the attributable risk. And then the population attributable risk, the incidence total population, which I would need to give you or you would need to calculate, minus the incidence in the unexposed or the non-exposed. If I don't give you the incidence in the total population, how are you going to calculate it? Everyone who got a disease, regardless if they were exposed or not, divided by your total population, right? Okay. Advantages of cohort studies. I will get a direct observation of the risk. This is the best type of observational analytic study that you can make in terms of estimating the risk. Well, now I'm not actually estimating, I'm calculating the direct risk, right? But your exposure factor needs to be well defined. You can have multiple outcomes too. And you can now have a temporal relationship between factor and outcome. So let's say I have a relative risk of 15, right? Great. My relative risk of 15 means that there's an association, right? But it needs to go with a p-value and a confidence interval. Let's say my relative risk is 15, but my p-value is 0.8 and my alpha level was 0.05. Is my relative risk actually statistically significant?
Can you say it again?
If I have a relative risk of 15, but my p-value is 0.8, where my alpha level was 0.05.
No.
No, it won't be statistically significant, right? Okay. Class, where do I have week 9? Okay. Now we go to the experimental studies, the other types of analytic, right? So experimental studies, we have all these different phases. We have an early discovery and ongoing research, which is mostly like the preclinical trial or the preclinical phase that is in animal models, right? Then we have phase 1 that I'm going to measure the safety and best dosage, right? I have very few subjects here in phase 2. I want to see how they respond to new treatment, right? I have a little bit more of people here. I'm going to test the effectiveness. Then on phase 3, this is where I start with my randomized control trials or experimental trials in general, because I have an intervention group and a control group, right? So I'm going to confirm effectiveness compared to other treatments that we said. And then we move to phase 4, in which everything went well, FDA approved, so now I can send it to the public. In phase 4, I won't have a control over the exposure. I won't have a control of over the environment. I don't know if they're gonna take their pills on time. I don't know if they're gonna mix it with alcohol. I don't know if they're going to, let's say I say that it's not recommended for people with diabetes. I don't know if a diabetic person is gonna take one, right? That I cannot control anymore. But we send it to phase 4 because we want to see what are the real benefits and best use in the population, right? So phase 3, randomized control trials, the one I can control. So the subjects are randomly allocated into 2 groups. Allocated is a very important word. I'm going to randomize, right? And with the randomization, that ends up with allocation of 2 groups, intervention and control, right? This is the most rigorous, highest level of validity type of study. Why? Because I control factors. I have less biases, but limited range of application, and of course, ethical implications. So, how am I going to help the bias? I'm going to blind either the subjects for single blinded or the subjects and the investigator for double blinded studies, right? What will that help with? Or which bias will that help with? Interviewer bias, Hawthorne bias, right? Hawthorne effect. You have a bunch, okay. And the measure of outcome, now we won't call it outcome anymore, we'll call it endpoint. Oh my gosh, that thing is annoying. What's the difference between a regular randomized control trial and a crossover study? That in the crossover study, my same subject serves as control and then as intervention after a washout period, right? And the quasi-experimental designs. So you have now in a community level intervention, right? My unit of analysis is no longer individuals, it's communities. I can manipulate the exposure factor. I may not have a control group. Most common one is fluor in water, right? Okay, challenges to validity of study designs, external and internal validity. What is the internal validity?
Can it be replicated?
Yes, exactly. So how well done was the methodology done, right? So I want all the details, all the I's to be dotted and the T's to be crossed. I want to be able to control for biases during these, like before, during, and after the methodology, right? But I want to be able to control for all of them and to tell the reader that I am controlling for them. External validity. Can I generalize the results? So your study could be the best. It could be so well done, but it could be to a very targeted population. So maybe it's not generalizable, right? It doesn't mean that the study is not well done. It just means that it doesn't have external validity, and that is fine. There's a lot of studies like that. However, you cannot have a study with external validity that doesn't have internal validity, because how are you going to generalize something that was not well conducted in the first place, right? Yes? Not? Yes. Okay. Thank you. So, what are the biases? Any errors that can happen? And these are because of the person that is doing them, whether that it's designing the study, that is collecting the analysis, the data, that is analyzing the data, that is interpreting the data. Okay, these are human errors. uh, it will impact your study. It will give you inaccurate results. So what we want to do is control for them, right? So selection bias is those in the process of identifying the study population and selection of subjects. And information bias are those errors in the measurement of the exposure or disease. Okay, so if you use an instrument that has not been calibrated, information bias. If you use a survey that was not approved and it's asking in English to people that only speak Spanish, information bias, right? So you have to be very detailed, because those we can control for. Oh, how do we control for selection bias? So we develop an objective case definition, we randomize, we make it very understandable, we ensure representativeness, and we aim for high participation rates, especially in what? Especially in cohort studies, when we know that we will have loss to follow up, right? How do we control for information bias? We blind, single blind, double blind, right? We make sure that the questionnaire is super clear. We make sure that the tests and the instruments that we're using are accurate, right? Okay, confounders. It's a third independent variable that will explain some or all of the relationship between the exposure and the outcome. So it can distort the effect, right? What are the criteria? This has to be present for a confounder to be there. It's associated with the exposure, it's associated with the outcome, but it's not in the intermediary. It's not an intermediary of the causal pathway, okay? And it can be controlled for in data analysis. So if I have alcohol consumption and heart disease, right? This is the relationship I'm looking for. Smoking could be a confounder both in alcohol consumption and heart disease. Age, one of the most common confounders, smoking and lung cancer. Age can be directly related to smoking and also um, directly related to lung cancer. So what I do, I control for it. How? In the inclusion criteria, I randomize, I match. This is for case controls, right? I match, let's say, for age. And in the analysis, I can stratify, so I can report per different ages. I can match the analysis. This is supposed to be a team matched analysis, or I can do a multivariate analysis. Usually, a logistic regression, right? A multivariate logistic regression. Some of you mentioned it in your studies. Okay. Week 10. Again, levels of prevention, right? Wait, what am I missing here? No, I have mentioned most of it. Confounders, variables, 2 by 2 tables. Okay, good. Screening, so secondary prevention, right? What do we want to do is use tests or other procedures to identify unrecognized diseases. Super important. They don't know they have the diseases, right? Because if not, it would be tertiary prevention, right? So it's applied to healthy population, seemingly healthy. They don't know they have something. Mass screening versus selective screening. Selective screening is when it's applied to high risk groups only, right? What is lead time bias? If I screen at this time at 55, I may end up with a 20-year survival, but that doesn't mean that there was more survival rates. It meant that I screened earlier, right? If I had screened at 65, I would only have 10-year survival, right? So the lead time bias, it's what makes it difficult to assess the effectiveness of screening programs. Okay, different types of screening tests and measures used in screening. So reliability. Remember, reliability synonym precision, right? So I want the test or the instrument to give me consistent results. I want them to be accurate, yes, but I want them to be always the same. That is reliability, getting the same thing more than once. And these, we're going to talk about intra-observer and inter-observer reliability. I want, when I do the testing, I want every time I do the testing to have the same results. And when I'm comparing my results to Alex, I want our results to be the same. Yeah? That's inter-observer. Validity, it's talking about accuracy. So the true measurements. This one is about getting it right. The true measurement is the gold standard, right? So I want something that is both valid and reliable. Valid because it's accurate, right? It's where it needs to be, and reliable because every time I do the testing, I get it on the right spot. What would be this? Reliable, which is precise, but I'm not getting it right. It's not accurate, right? And this one, not reliable nor valid. It's all over the place and never right. Okay. A new 2x2 table. In this one, I'm going to be measuring the validity of a screening test compared to what? To the gold standard, right? Okay, so I have, on this side, I have my test results, positive or negative. This is what I'm trying to, this is what my test is, right? And this is what I'm going to compare it to the gold standard. The gold standard is going to tell me if someone, like if a person really has a disease or not, okay? And then I'm going to compare it with my test results. So sensitivity. Sensitivity will be that ability of a test to correctly identify screen individuals who actually have the disease. Who do I know who actually have the disease? With the gold standard, right? So it's going to be my true positives of people who tested positive within my test, and I'm going to compare it with all of those who really have the disease according to the gold standard called true positive rate. Specificity, true negative rate. So now it's the ability to correctly identify individuals who do not have the disease. So now who am I going to see? Those who tested negative in my test, right? Divided by those who really do not have the disease according to the gold standard. Yeah? Positive predictive value. Now I'm going to see the proportion screen positive who actually have the disease. So now I'm going to see within my test what is the real probability that someone will test positive within my test again, right? So it's going to be my true positives against those who tested positive within my test. Yes? And this one is impacted by prevalence. So if I have low prevalence, I will have a low positive predictive value. Why? Because I can expect my A to be low, right? Because if I have a low prevalence, all this column is going to be low, right? So that means that my true positives are going to be low. And if I have low numbers, I'm just going to have a low positive predictive value. But if I have a low prevalence, that means that I have a larger number on the negatives, right? So my negative predictive value will go up. What is a negative predictive value? The proportion screened negatively who actually do not have the disease. So it's going to be my true negatives divided by all the negatives in the test result, because it's within my test that I'm comparing to, right? Okay. What I want to do is decrease the number of false positives and false negatives, right? And then this is a summary. Okay. The policy arena. What's our goal? Health promotion, right? Disease prevention. So what are we going to do? We're going to use evidence-informed data, which is the scientific evidence plus all the other community views. We're going to ask people, we're going to talk to people, we're going to talk to politicians, we're going to see what's out there, just not just the research part. We're going to, like the scientific research papers, we're going to look at everything as a whole, right? So what is the multiple streams framework? And this is, of course, part of the exam. We have 3 different streams: the problem stream, which defines a situation; the policy stream, in which the policy actors propose a solution; and the politics stream, in which both are taken into account and a policy is made. For it to happen, we need to have a policy window, right? All 3 have to happen at the same time for the policy window to happen. This was the extra credit if you still want to do it. Go to Healthy People 2030, choose one topic as your problem, okay? See what policy or law or mandate has been done. See if you find the status of that problem. It can be decreased, it can be decreased. And then based on what, okay? Based on what type of data you can say that is decreased or increased.
Have you
And
posted it, the extra credit?
well, I posted the whole um
I saw something about this on the assignment part, but like there's no place
yeah.
to like submit the thing.
Okay, let me open something up. So I think I closed it or hide it. I don't know. So open extra credit. Okay. What can we do? Learn, investigate. Advocacy versus lobbying. What was the difference? This is from the homework. What was the difference between advocacy and lobbying?
Uh, Advocacy is one type of lobbying, and like lobbying is just like in general, like more like
Mm-hmm.
a general term.
Okay, perfect. Uh, Advocacy, you want to know the audience, know the issue, build your team, right? You need to care. And so I will do something very similar to this classwork where I give you an excerpt. I won't give you the whole article, of course, but when I give you an excerpt, you should be able to tell me what goes in each policy stream of the framework, okay? And then you may want to see the differences between advocacy, lobbying, the types, the levels, blah, 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 blah. And oh, and then infectious disease. make sure that you do the module because there are questions about that infectious disease module. Okay? Questions? No questions? You're all good with the topic? Well, let me stop recording first.